Thank you, Kirsi. I'm delighted to see you all here. Welcome on behalf of the School of Science as well. This is going to be a really exciting event. It's the third time they're having it, and I was here last year, and it was really, really great. So anyway, why I'm talking about computer graphics. Computer graphics is the technology behind games. Everything you see on screen when you play a game is the product of computer graphics, okay? My own background is in games as well. I worked on graphics technology for Remedy for quite some time, had my hands in Max Payne and Alan Wake. After I did my PhD, I went to MIT to do research in graphics for a couple of years. Then I joined NVIDIA Research in Helsinki, which is where I also work today. And in addition, I'm the first ever professor in computer graphics in Finland. So let's look at what modern real-time graphics looks like. This is a short clip from Killzone Shadowfall running on PlayStation 4. And we're seeing some really beautiful vistas with large numbers of objects and realistic lighting effects, reflections, atmospheric effects, lens effects, stuff like this, really complex geometry, all rendered in beautiful real time on a PlayStation 4. I hope you can see at least somewhat what's going on, despite the fact that it's pretty light out here. So that's what modern real-time graphics looks like. Exhibit B is you are going to see this animation later on today in Ralph's talk, but I'm going to show you a brief glimpse of what the absolute highest quality of graphics being produced in Finland today looks like. And so this is a sequence from Remedy's upcoming Quantum Break. Now we have more light. I think we'd actually need a little less. And so this is an Xbox One title. That's I'll let the guys tell when the release date is. I'm not going to try and venture a guess. But anyway, this is this I feel represents the absolute top tier of production values and graphics technology in games today. And I'm really proud that they're doing this stuff in Finland. So anyway, what does graphics mean? In order to render or synthesize using a computer pictures that are satisfyingly complex, we need three things. We need complex geometry, what shape things are. We need complex shading, what color they appear to be. And then we need to be able to figure out in a large environment consisting out of lots and lots of objects, what's actually visible in our picture. And this computer graphics is really, you could divide it in three parts, the first of which is modeling. It just says, in order to draw a picture of a place that does not exist, you need to tell the computer what that place looks like i.e. you need to specify what is in the world. You need to model the world, either by hand using artist manpower, or increasingly by scanning real-world objects using cameras and lasers and these sorts of things, which is really cool. Then, of course, static scenes are not very interesting. You need to make it move. You need to animate your characters, make them run, do things that create compelling experiences and tell stories. And then finally, once you're done with all this, you need to tell the computer, okay, you have 30 milliseconds, draw this on your screen. And this process is called rendering, which just means let's take the state of the world as it is right now, the geometry where the camera is, where the lights are, et cetera, and then draw a picture. And that really means figuring out at each pixel in your image what's there and what color that thing is. Simple as that. So how do you actually get to know how to do all this? At Aalto, we teach graphics in two classes, an introductory one and an advanced one. And in the intro class, which runs every fall, it's going to give you an overview of all the things that go into graphics: modeling, animation, rendering. And in the advanced class, we take a deep dive into some of the more advanced concepts. Like last year and this year, we're looking at realistic rendering, i.e. how you actually create pictures that are physically based or simulate the physical propagation of light in order to create the utmost realism. And so the intro class, which I really hope a lot of you are going to come and take next fall, will teach you, give you an idea of pretty much everything that goes into that kill zone frame or into that quantum break frame. At least some level, you'll have an idea of all of the technologies and things and how they actually work that you need to do in order to draw that picture. And you will have an idea of what the graphics processor or the GPU in your computer does in order to draw that picture. And you will code a lot on your own. You will actually create your own implementations of lots and lots of algorithms, including modeling things like subdivision surfaces, which is the basis of all modern rendering. You will create character animation, skinning. You will do even your own physical simulation like cloth and so forth. Simple versions of all of these, but still, the real deal. And in addition, we'll do rendering using ray tracing and also writing real-time shaders, which is how real-time graphics works. In the advanced class, the topic varies. As I mentioned, we do indirect or physically based lighting this year. And I should mention that the first time I taught this last year, the class got by far the best anonymous student reviews out of all of the 70 or so computer science classes that are offered at Aalto. I hope we're going to exceed that, get better scores this year, but we'll see. It is kind of hardcore. We do a lot of math and algorithms, but in the end, if you make the effort and actually try and wrap your head around all that math and all those algorithms, then you'll be actually able to create pictures that are convincingly realistic. And we'll also do this in real time. So I hope you can see here we're rendering indirect illumination from a moving light source in real time. Okay. Anyhow, you will code a lot, but it's fun. And in addition, there are prizes to be won. For instance, in the intro class last year, we had the 3 best students visit Remedy on a private face-to-face with the technology people. One of those guys works at Remedy right now, so that's pretty cool. The 6 best this year are going to get the similar treatment, and we also have other prizes. And NVIDIA is donating GPUs for the final competition in the advanced rendering class, GeForce Titan, which is a really, really beefy GPU. And actually, the student who created the most impressive code last year is now working with us at NVIDIA Research, doing his master's, and is going to go on to University College London, which is one of the best universities in the world, to do his PhD in graphics, which is also pretty cool. And the guys who judged these competition entries in the advanced class, last year we had the rendering research director of Weta Digital, the people who do The Hobbit and these kinds of things. So if they don't know how to do something, they ask this guy. And he judged the competition entries. This year we'll have Eric Tabellion from DreamWorks Animation, who is the guy who brought indirect illumination into the animated feature film industry in Shrek 2. And he will, take a look at the entries and pick a winner. Okay, so that's education. What do we do for research? Research means picking problems that are important enough that some people care and trying to be better at it than anybody else in the world, okay? And one thing that we're doing, this is my PhD student Mika Aittala's work. We're modeling the materials of real-world surfaces, which are very important for realistic appearance in, say, games. And they're very hard to do by hand. So what we do is we take a material sample, we put a monitor above it, we show some patterns on the monitor and take pictures. Then lots and lots of number crunching happens. And then in the end, we get out a result that when we compare it to photographs, this is a crumpled piece of paper with some tape on it, and then we feed the data that comes out into our real-time rendering engine, we can actually reproduce the appearance of these real-world surfaces really well. And I'm going to skip that and say that we know how to do this better than anybody in the world. And the results are so nice that the prototype system is in use at Remedy right now. And what comes out is a set of texture maps that describes the appearance and can be fed into any modern real-time rendering engine. Another example I'm going to show you is physically based character control, which is a really hard problem. Here I'm showing, Sorry about that. Okay, now I have no way of controlling the animation. I'll just go back and say, if you have a physically based character in an unpredictable environment, you know, he's being hit and slapped and so forth, creating animations that respond to all the possible ways that he could be hit is totally not realistic at all. And what we're doing here in Perttu Hämäläinen's research is we are actually using a brute sort of very hardcore real-time optimization system that makes the character balance when he falls over, and so this is based on a sort of very hardcore artificial intelligence in the sense that there's no animation of any kind being done to create these effects. So the character has not been told what to do when he gets hit from a certain point and so on. And again, this is one of the things where nobody in the world knows how to do this better than we do, which is pretty cool. So there was a poor explanation of what's actually going on there. But if you're interested in this thing, you should ask Perttu for thesis positions. And that's what I have. This is my website. Graphics is exciting. Come learn graphics with me and you know, take off. Thank you.